resolution office in the Pentagon, and I asked them, do you see anything? Because they claim they looked at all the reports within government, they have access everywhere. And they said, so far, we haven't seen anything unusual except for some reports from FBI agents that do not have quantitative data. That's what they said. A dozen craft with pilots in them and so forth that the government has, and they gave it to corporations. And
Yeah.
Did you know that over 90% of the universe is made of matter we cannot see or fully explain? Yet, paradoxically, we can stream high-resolution images from Mars online in minutes, while vital data from a mysterious interstellar visitor has been missing for 45 days. On November 13th, as the world celebrated NASA's latest Mars images, an uncomfortable question emerged. If streaming Mars data is so fast, what's going on with the 3I/Atlas images taken on October 2nd? 45 days later, they remain unreleased. These images were captured by HiRISE, the highest resolution camera ever to orbit Mars, operated by the University of Arizona. With today's computing power, that data should have been public long ago. This delay has sparked public curiosity and serious questions. Is something being intentionally withheld, or is this just bureaucracy at work? When I was asked if I believed NASA's explanation, I smiled. I didn't dismiss it, but I also didn't accept it blindly. The truth, whatever it is what matters. And while we cannot claim a deliberate cover-up, the layers of complexity behind the release of scientific data can make it appear that way. 45 days is a long time in a world accustomed to instant updates. The key fact sends chills. The photo was taken on October 2nd, yet not released until November 13th. That gap alone raises eyebrows, but the science itself is now even more compelling, because in the meantime, 3I/Atlas has changed dramatically. Observations over the past weeks show that this interstellar object has begun forming a dust tail at an unusual rate, evolving faster than existing models predicted. What started as a faint, patchy streak has now become a sharp, high-resolution dust tail captured in newly released imagery. Scientists are now rethinking their fundamental assumptions about interstellar objects almost simultaneously across multiple teams. Adding another layer of intrigue, radio astronomy networks reported a brief, unverified pulse near 1,420 megahertz, the hydrogen line, a key frequency in deep space surveys and programs searching for extraterrestrial signals. While this signal is yet to be independently confirmed, its timing coincides with the period of increased Atlas activity, forcing scientists to scrutinize every piece of data. Naturally, this fuels speculation and conspiracy theories about one of the strangest objects to pass through our solar system. The situation continues to evolve rapidly, with researchers monitoring each update closely. 3I/Atlas is only the third interstellar object ever confirmed to enter the solar system, and since its discovery months ago, it had behaved almost exactly as expected. Until now. Suddenly, everything we thought we knew about it is being questioned. At first, 3I/Atlas appeared faint, slow-moving and largely featureless, a cold, icy remnant drifting silently inward from a distant star system. But over the past few weeks, its behavior has begun challenging every assumption we have about interstellar ice in sunlight. The first hint of something unusual came in the form of a column of material pointing almost directly toward the sun. This is highly unusual for comets. Typically, solar radiation pressure and the solar wind push dust and gas away from the sun, forming the classic cometary tail. Atlas, however, seemed to be pushing material toward the light source, creating an asymmetrical, truncated structure that left observers scratching their heads. This counterintuitive emission pattern suggests that the material might be escaping from a localized vent or a deep fissure in the comet's core, rather than being a uniform sublimation across the surface. Even more puzzling, this blunt, dense jet remained remarkably stable over multiple observation periods. It did not spread, fade, or fluctuate rapidly as most cometary outgassing would. The consistency of this jet defies conventional models. Astronomers are now asking, is this simply a strange outgassing phenomenon caused by the comet's shape? Or is it revealing a deeper mechanism we've never documented? The debate has spurred bold speculation in the community as teams scramble to understand this anomaly. Then, almost overnight, Atlas dramatically changed its appearance. Observations from large aperture telescopes in the southern hemisphere, particularly in Chile and South Africa, revealed that the previously sunward-pointing jet had reorganized into a more familiar cometary tail, extending away from the sun in alignment with classical dynamics. What stunned astronomers was not just the change in shape, but the speed at which it happened. The comet's structure shifted so quickly, it appeared as though some force had ripped material from its core almost simultaneously, leaving even veteran researchers in disbelief. The physics of this event deepens the mystery further. Photometric and spectroscopic analysis revealed that the dust ejected from ATLAS is unlike anything typically observed in solar system comets. Instead of ultra-fine, micro-sized particles, ATLAS is ejecting relatively massive dust grains, up to 1/10 of a millimeter in size. That's enormous for interstellar dust. Even more striking, these heavy particles are being released in a steady, continuous stream at just a few meters per second. There are no explosive sublimation events, no chaotic collisions, no signs of violent activity typical of comets. Instead, the ejection pattern is slow, disciplined, almost deliberate, as if the comet's core is denser, more cohesive, and potentially layered, with each layer reacting differently to solar heating. This is not just a comet behaving oddly. 3I/ATLAS is rewriting what we thought we knew about interstellar bodies. Its core may be more structured, more resilient, and far more mysterious than any comet we've observed before. This has scientists asking a fundamental question. Is 3I/ATLAS simply an unusual icy object from a distant star system? Or is it evidence of a physical mechanism we've never seen in our solar system? Things became even more perplexing when spectroscopic measurements revealed that gas from ATLAS began sublimating at 3.5 astronomical units from the sun, far too distant for water ice to evaporate. At such cold temperatures, only extremely volatile compounds like carbon monoxide or carbon dioxide could undergo phase transition. The strength and timing of this activity strongly suggest that ATLAS contains a rich supply of volatiles, formed in the icy outskirts of a star system, regions that have been near absolute zero for billions of years. Unlike our own solar system's Kuiper belt or Oort cloud, ATLAS did not originate locally. It came from far beyond our stellar neighborhood. Then came an even stranger development. Reports began circulating that radio astronomy networks had detected a brief, pulsing signal near the 1,420 megahertz hydrogen line. This is not just any frequency. It is remarkably quiet, low in interference, and has long been considered by SETI researchers the ideal channel for any civilization that wants to be noticed. The coincidence of this transient signal with the unusual activity of 3I/ATLAS has drawn attention from scientists across the spectrum. Even the most skeptical researchers are following every new data point closely. The signal itself was fleeting, lasting only a few moments and recorded by only a handful of independent observers. No scientific verification has confirmed its origin, and it could easily be technical noise, terrestrial interference, or an unrelated phenomenon. Yet the timing is compelling. It coincided with a surge of activity from ATLAS, prompting radio observatories worldwide to continue scanning for repeats. Meanwhile, ATLAS itself is changing rapidly. Its tail is growing longer, its brightness is fluctuating, and the structure of the dust and gas is evolving. These observations suggest the nucleus may host multiple active regions, each releasing material independently. This offers an extraordinary opportunity to study how an icy, interstellar object reacts as it approaches the sun. ATLAS may develop a strong coma, exhibit surface fractures, and produce new dust bands, all phenomena that could reveal insights into its structure and history. Compared to the two previous interstellar visitors, Oumuamua and Borisov, 3I/ATLAS is strikingly different. It exhibits larger dust masses, rapid structural changes, and unusual gas behavior, making it arguably the most significant interstellar object ever observed. Scientists are racing to gather data because the comet could fragment as it nears the sun, destroying its original form, but simultaneously exposing material that has drifted between the stars for millions of years. Observatories across multiple continents are now collaborating to monitor ATLAS almost continuously, ensuring that no critical event goes unrecorded. Each type of telescope provides a crucial piece of the puzzle. Optical telescopes track changes in brightness and tail shape. Infrared instruments reveal the hottest regions where sublimation is most active. Spectroscopy identifies the super volatile molecules characteristic of interstellar material. Meanwhile, radio telescopes continue to monitor for rare molecular emissions and any unusual signals that coincide with Atlas's heightened activity, building a rare radio archive for an interstellar comet. When these datasets are combined, scientists expect to construct the most detailed profile ever made of an interstellar object, far surpassing the level of analysis available for Borisov or even the enigmatic Oumuamua. If Oumuamua raised questions and Borisov set a benchmark, 3I/Atlas could unlock a deeper understanding of the diversity of objects wandering between star systems. The growing wealth of observations will allow researchers to map how Atlas sheds dust and gas over time. Changes in the tail reveal its rotation period, pinpoint active regions, and uncover the structure of the coma, where escaping gas interacts directly with radiation and the solar wind. Even subtle fluctuations in brightness could signal that the nucleus is elongating, becoming asymmetrical, or beginning to fracture. This is particularly important because 3I/Atlas represents a type of object, ejected from its parent star system, wandering through the galaxy for millions of years. During that journey, its surface was eroded, its composition altered, and its internal structure reshaped by countless micro-collisions. Now, as it enters a new star system, thermal shock and exposure to unfamiliar radiation could trigger behaviors never before observed in our solar system, offering a unique opportunity to study the evolutionary history of icy matter across the galaxy. The scientific community is watching with unprecedented attention. Whether the reported radio pulses are genuine or a technical glitch, the phenomena Atlas displays are extraordinary. An unusually fast-moving dust tail, rare, heavy, and uniform dust grains, and the early sublimation of highly volatile materials all point to a complex, layered structure formed under extreme conditions. This raises a critical question often overlooked. Why does an object that should be chaotic appear so organized? Consider the geometry of the sunward-facing jet before it collapsed into a tail. In fluid dynamics, a coherent jet over a distance requires a nozzle or a defined exit geometry. Could Atlas's layering be the result of structured planetary processes? Or, as some daring theoretical models propose, even artificial engineering, the uniform release of heavy dust grains moving at slow, controlled speeds, hints at a low-gravity environment or a mechanism regulating ejection rather than random sublimation. This isn't just physics. It's a cosmic detective story written in the language of the stars. As 3I/Atlas continues its approach to the Sun, experts predict that its rate of activity and structural evolution will only accelerate, offering a rare chance to witness, in real time, the behavior of a true interstellar wanderer. Jets may erupt from newly formed cracks, tail structures might shift or branch, and unexpected patterns of radiation, from infrared to radio, could emerge. For scientists, this is a golden opportunity, a chance to observe the behavior of a powerful interstellar object up close. But for the superpowers competing in the space race, 3I/Atlas represents something else entirely. In the context of strategic competition, any unusual signal or unexpected activity from Atlas becomes a focus of speculation. Commentators in the United States and elsewhere have raised the question, are certain nations watching Atlas more closely than they admit, or even attempting to exploit its data ahead of rivals? Some have suggested that if Atlas were to produce a repeating signal, natural or otherwise, it could be interpreted strategically. History has shown that anomalies in space are rarely ignored, and even natural events can be treated as intelligence opportunities. Others have speculated that if Atlas's orbit shifted due to a strong outgassing event, nations might use the phenomenon to test early warning systems or monitor orbital dynamics in real time. In an era of rising space militarization, no detail is too small to observe, but all of that is secondary to the scientific truth. A tiny, ancient traveler from a distant star system is revealing its history right before our eyes. Every new image, every spectroscopic reading, every subtle change in the comet's coma brings us closer to understanding the universe through the lens of an object that has wandered the galaxy for millions of years. Atlas is both a mystery and a gift. Each alteration in its behavior is a clue to a much larger story, the story of matter in our galaxy and our place within it. The lesson here is simple but profound. Science is not about fitting new observations into old boxes. It is about having the courage to build new boxes when the data demands it.